Good morning, everybody. Today I am going to discuss three important things. One, density of state. Two, why it is important. Importance. Three, carrier transport phenomena in semiconductor. Okay, today I am going to discuss density of state. Okay, first, then I will discuss why this density of state is important. Third, I will discuss the carrier transport phenomena in semiconductor. Okay, now in the last class we have number of microstate. I will compare number of microstate in between momentum 0 and p. This is I have already discussed in the last class. The value of number of microstate is sigma p is equal to how much we are getting? TSP 4 pi v p2. Equation number, suppose this is 1. Okay, this represent number of microstate in between momentum 0 and p. Okay, now I am going to, in order to calculate the density of state for specific particle, first of all you must have some idea about what are the particle available in the universe. Okay, whole particle. Okay, I am removing this part again. Okay, the part in particle physics, whole particle is divided into two parts. Particles divided into two groups. One is known as a fermion and boson. The whole particle in the universe is divided into two groups. One is known as a fermion, one is known as a boson. So depending on what? Depending on the spin value of the particle. If the spin of the particle is half integral, half n means 1, 2, 3, 5, something like that, not equal to 0. Okay, n equal to 1, 2, 3, 4, 5. For example, if we talk about electron, then spin of electron is always represent half. And remember, the unit of spin is always in h cross. H cross also unit of angular momentum. Clear? Because J equal to n h cross, n is a number, so h cross the unit of angular momentum. This is a numerical value. So angular momentum must have the dimension of h cross must have the dimension of angular momentum, and h cross is the unit of spin. Okay, remember. And integral spin means you can express n h cross also, because h cross we never write, because we know the unit of spin is h cross. We always represent n means integer value. The spin particle that have the spin, suppose integer spin was 0, 1, 2, 3 like that. These are particle having this type of spin, integral value 1, 0, h 2, 3, 4, 5. These particles are known as a boson. Okay, and fermion are only those particles whose has the spin equal to half, 3 by 2, 5 by 2, something like that, 7 by 2. These all are fermion. Now this density of state will be different for fermion as well as boson. That's why I am giving you basic idea about the classification of the particle depending on the spin. Clear? Okay. Now this is a basic idea. Now this is the number of microstate in between 0 and p, momentum 0 and p. Now my focus is to convert this number of microstate in terms of momentum. Now case 1, suppose if I want to express the number of microstate in terms of energy, then what I am putting. So that is why for classical particle, or fermion, say electron electron, proton, these are the fermion because their spin is half integral. Okay, half is cross. So these are fermion. Then what happened? We can express energy equal to p square by twice. This is why it is called classical particle, because we have not incorporated the relativistic correction. Okay, that is this is simple equation. This is E equal to half mv square. It is derived from here. Okay. Now, if I replace P equal to how much? Twice me T by 2. Is it okay? Oh, sorry, half. P equal to half. So if I put this value here, then number of microstate in terms of energy, 4 pi v T s cube twice m e T by 2. Is it okay? This is number of microstate in terms of energy. This is my number of microstate in terms of momentum. Clear? Okay, you can transform here to there and this to this. Do both vice versa. Now, now next we are going to calculate density of state. This is the number of microstate. Now I am going to calculate density of state for fermions or bosons. Density of state. This is for case 1. Okay, case 1. No need to density of state. How to calculate density of state for classic under case 1. Okay. No. First of all, I simply write that this expression again. This is a number of microstate. 4 pi v T s cube twice m e T by 2. Okay. Now density of state. This is the number of microstate. Density of state is represented by ZE. Okay. ZE D. You can express D equal to differentiation of this equation. Just differentiate the equation 2. Equation 2 differentiate. Sigma E with respect to D into D. Simple. Just differentiate this equation. You will get the density of state. Then if I differentiate this equation, 4 pi v T is cube, then 2m T by 2, just differentiate, E half D. Is it okay? T by T cancel, 2 cancel, 2 equal to 2 pi v is cube twice m T by 2 E half. This is no need to remember, it is very easy to remember. So if I divided by V, GE by V DE equal to what is the value? Twice pi is cube twice m T by 2 E half D. Okay, this is the density of state. Simply write Z prime E D. Okay, is it visible? I don't know. Okay. This is the density of state. Is it visible? Okay, I am not writing this part. I think it is not visible. So I am writing here this step ZE by VD. V is the total volume. Okay, total volume, Cartesian volume, equal to twice pi V, or not V. V is already removed. H cube twice m T by 2 E half e to the power half d. This is the density of state. We simply write Z prime d equal to 2 pi v h cube twice m T by 2 E half d. Is it okay? This is the density of state. Now what you can understand? The density of state, I can tell you G. This is the density proportional to E half. Forget about the constant. This is for this density of state is valid for classical particle or fermion, not for boson. So why it is important? I am telling you. In semiconductor, there is a two type of carrier. One is electron, one is hole. Both are fermion. So we have to know what is the density of state in order to calculate the number of carrier in semiconductor. How it is important, what type of calculation involved, I will tell you after finishing this part. Okay, case 2. This is a density of state for fermion. Case 2 for boson particle. But here in case of semiconductor, boson is not required, but even though I am telling you the general formula. For in case of the, suppose this system is composed of boson particle, then density of state will be different. Suppose boson, say photon is boson, or phonon is also boson. Photon is associated with the electromagnetic radiation. When you talk about electromagnetic radiation, you have to understand we are talking about the photon. But when you talk about matter wave, solid matter wave, sound wave, something like that, matter wave, when you talk about a matter wave, sound wave, then you have to understand we are talking about the phonon. Both are boson, both have an integral spin, okay, not half integral spin. In that case, and rest mass of both is 0, so we have to know p square by c square, m naught c square, c to the power 4. Now rest mass is m naught rest mass of photon. In case of suppose photon is 0, so this equation pc. So initially in previous case 1 we are replacing E equal to p square by twice m. This equation does not valid for photon. Okay, in case of photon or phonon, we have to replace this equation. Energy equal to E. Then we know this. Then number of microstate sigma E is equal to how much? 4 pi v by 3 s cube. And in terms of P, we are replacing this one in the E equal to E by C cube. Is it okay? This is number of microstate in terms of energy for boson particle. Clear? So density of state. Now density of state. Case 2 density of state. Density of state will be like, what is the density of state? GED equal to just differentiation of this part. D. Differentiation of this one into D equal to what we are getting? 4 pi v s cube c cube e square. Is it okay? Similarly to the previous calculation, if I divided v, then g prime d equal to 4 pi s cube c cube e square. D is also there. D. So what do you understand? G e prime proportional to e square. See, in case of photon or classical fermion, in case of photon, the classical particle fermion, the density of state proportional to half. Here is E proportional to E square. That means density of state is depend on nature of the particle. If it is fermion, then it will be different. If it is boson, it will be different. So finally, what we understand. So then these are the equations. So for fermion, I am again summarize fermion. Density of state G, we are getting 2 pi v. V is not there. A is cube. Twice m. T by 2. E half. Okay. This is density of state. And for boson, G, I am writing only G, not removing the D both sides. Okay. G equal to 4 pi S cube C cube E square. So see, this is the difference. So one is proportional to, here is proportional to E half, here is proportional to E square. So density of state depends on, both are, remember, both are three-dimensional case. So that means density of state depend on the nature of the particle. Okay. So nature of the particle is characterized by what? So I am giving a general formula for, in order to remember, shortly remember general formula. Density of state, forget about these are the constant. We don't need to focus on constant so much. We have to remember the variable term. This term is very, very important. So density of proportional E d by S minus 1. This is the general formula I am telling you. You never find in a book, but you remember this is then D is the dimension, S is the integral value which is obtained from dispersion relation. Now you have to know what is the dispersion relation. This is, remember the general equation. This is the general equation. Okay, general equation. D is the dimension. If it is 3 dimension, then D will be 3. S from where you are getting S. Now dispersion relation. This S for the value of S you can get from the dispersion relation. Dispersion relation. From where you will get it? Dispersion relation omega versus K. Omega versus K. Omega means what? Omega is the angular frequency associated with any wave or any particle. When you talk about electromagnetic wave, then you have to understand omega is the frequency associated with a photon or electromagnetic radiation. But when you talk about matter wave, or then you have to understand omega is the frequency associated with a matter wave, sound wave suppose, or phonon. Okay. And K is the wave vector, is give the propagation vector. The direct, it will give the direction of in which direction wave is propagating. Okay. So omega in case of C, in case of here, and another relation. This is you have already studied here. Another relation, omega versus K relation, or P versus K relation is known as a dispersion relation. And this dispersion relation will tell the behavior of the particle, whether it is photon, whether it is boson, how you see E equal to P square by twice M. Clear? So now P means P is the momentum H cos K. Remember H cos K, and K equal to twice pi by lambda. Remember this is the value. P momentum equal to H cap into K. K is the wave vector, and K is the twice pi by lambda wave vector. Okay. Now if I put E equal to H nu, you can say H omega. H cos omega means energy of photon. Okay. And T equal to H cos square K square twice M. Means omega proportional to K to the power 2. Is it okay? K to the power 2. This 2 is known as this is called S value. Value of S. S means power of K. S is the integer value which represents the power of K. Okay. That is in case of case 1 for fermion. Okay, fermion we can verify right now. So what I am writing general formula, G proportional to E d by S minus 1. Okay, proportional E, D means dimension. This equation is valid for 3 dimension. Now we are considering 3. D dimension is 3. S value is say S value 2 minus 1 proportional to E half. Is it okay? Millisecond is verified. Okay. Similarly, in case 2 we are talking about photon. Photon, what relation we are getting? E equal to PC. Is it okay? E means H cos omega. P means H cos K. C. That means omega proportional to K to the power 1. S single. There is no power means single 1 S or value 1. Okay. Now you can verify. This is in case of case 2 photon or boson particle K equal to 1. Boson means photon. So general formula G proportional to E. This is in 3 dimension. If it is 3 dimension, then D equal to 3. If it is 2 dimension, D equal to 2. That 2 dimension, 1 dimension calculation I will not discuss here because you have to study again in 4th semester, 5th semester, 6th semester. Then I will teach you. Then 3 by 1 minus 1 proportional to E square. Is it okay? Now it is C. It is max. So instead of remembering both equation independently, you remember the general formula. Okay. This is why it is important. Now I am going to why it is important. This density of state, why it is so important, I will tell you right now. Importance of density of state. Suppose if you consider this is a cube. This is a solid cube, suppose, something like that. This is a cubical box, solid box, just sugar cube. Okay, if again you listen very carefully, this is sugar cube. This box contains n numbers of particles. N numbers of particles. Okay, this is n numbers of particle, 1, 2, 2, 2, n numbers of particles. And energy of each particle, is h cross omega. Or total energy, I can represent like Planck blackbody radiation, I can represent n h cross omega. Okay, this is the total energy of the system, and energy associated with each particle is h cross. Then total energy is n h cross 1, 0, h cross, twice h cross, something like that. So this is the total energy of the system, energy associated with the h omega. So now my aim is to calculate average number of particles inside this box. What is the average number of particles? How to calculate? N e to the power minus beta e summation e to the power minus beta e. This is the formula, you remember. In mathematics, have you remember? I don't know. When you calculate average value of x, then how will you calculate? Sum of n, ni, sum of ni, xi. Have you remember this formula in mathematics? Ni, xi. Ni is a number, xi is a x1, x2, x6 like that. This is in mathematics. But here, in microscopic calculation or statistics, you have to calculate average number like that. If it is n, then it will be n. If it is x, then it will be x. Okay? But in quantum mechanics, if you expectation value, if you calculate expectation value in quantum mechanics, then you have to do like this. Okay? Same formula. If it is x, if it is suppose n, then in quantum mechanics, this is in quantum mechanics. This is in statistics or condensed matter physics, thermodynamics, you have to use this calculation, microscopic calculation. Okay. Then, if I put this value, sum of n e to the power minus this value, n h cross omega beta, e to the power n h cross omega beta. Okay. Or you can, h cross omega beta means you can express it like that, n e to the power minus n is nu beta. You can write nu also, nu frequency. E to the power same thing. E to the power n is nu beta. H cos omega means what? H by twice pi into twice pi nu. Twice pi cancel. So H nu. Same thing. H cos omega H nu. Same thing. Okay. Now if I take this value, can I write like this? E to the power minus H nu beta to the power n, then n e to the power minus H nu beta to the power n. Is it okay? I am removing this part. Okay, I am removing this part. So what I am getting, average number of particles inside this box equal to n summation n e to the power minus H nu beta to the power n. Same thing. Okay, sum of e to the power n, n is not there, H nu beta is constant, equal to 1 by kt, equal to, if I put this equal to x, then what is the value? N, this is n. Okay, this is n x to the power n, x to the power n. I am putting this value, x equal to e to the power minus H nu beta. I am considering this value. Then first one is what? N is goes to 0 to 1. Okay, n is goes to 0 to n. First one is infinity, very last 0. So first one will be 0, second one 1x, twice x square plus like that, 1 plus x square like that. Okay, this is equal to binomial series. If you remember, is this, if I take 1 minus x to the power minus 2. If you see the binomial series in high secondary books, So finally what I am getting? x1 minus x. X means what? Put this value e to the power h nu beta. Okay, 1 minus e to the power h nu beta. So if I divided both numerator denominator by this term, then what you will get? 1 by e to the power h nu beta minus 1. Okay, 1 by e to the power h nu by kt. Okay, kt minus 1. This is the average number of particles. Now you see, if I modify this equation, what I am getting here, what I am getting an average number equal to 1 by e to the power h nu by kt minus 1. Okay. So if I write 1 by e to the power e, this is simply e minus mu by kt. You may ask, this is not plus, this is kt. This I am adding one term mu. Mu is chemical potential. Mu is equal to 0 for boson. I don't know whether this box contain particle which may be boson, which may be fermion. I don't know. That's why I modify this equation. I am adding mu term. Let's say if mu is 0, mu not equal to 0 for fermion. So this function, this is the probability function we represent Fe. Okay, if it is fermion. If it is boson, this is fermion. Fermion mu not equal to 0. I mean, if it is boson, then mu equal to 0, then this equation becomes this one. Then it will be Bose-Einstein function. Boson. Okay, this is known as a probability function. So average number means probability function. Now this is for this equation. This is Fermi function. Okay, remember this Fermi function. If it is mu not equal to 0, if mu equal to 0, this is known as a boson. Remember. Now total number of particle, small number of particle is equal to G dA into average number of particle. Okay, so total number of particle n in the box equal to integration of G dA into average number. Average number means what? G dA into average number means F. Now, if I know this, suppose this box is a semiconductor, then we know that a semiconductor contain either electron or hole, both are boson, both are fermion. Then you have to replace this equation mu not equal to 0. Okay, if the system composed of particle like photon, then mu equal to 0, you replace this value. Suppose now I am going to calculate the total carrier concentration in semiconductor. Suppose electron, then what I will do. What I am getting for electron or fermion density of state, G equal to what is the value? G d equal to what I am value getting? 2 pi v. Is it okay? 2 pi by h cross twice m t by 2 e half d. Is it okay? This is the for electron. Suppose this cube is contained. Suppose this cube is considered as a semiconductor. Then it will be fermion or classical particle. Then we have to replace density function. So 2 is constant, h cube is constant, twice m t by 2 is constant, integral e half, that Fermi function will be 1 by e to the power e minus mu by kt minus 1 d. Now if you do the integral, then you will get the total number of carrier or electron in semiconductor. And similarly you can calculate total number of hole in semiconductor. Okay, that's why density of state is simple. Okay. Now next part. Next I am going to carrier transport phenomenon. Carrier transport phenomenon. This is the basic idea of semiconductor. That if we understand this part, then remaining calculation in semiconductor, whether TCU, transistor, or operational amplifier or hybrid circuit, then you can easily understand the internal mechanism of transistor. Transistor is nothing just combination of semiconductor. So if we know the basic mechanism of semiconductor, we can easily understand the basic mechanism of transistor. That's why I'm teaching and more giving more focus on this basic part. Okay. In semiconductor, this is suppose semiconductor. Semiconductor electron and hole is there. In semiconductor, there is a two carrier. One is electron, one is hole. So total carrier concentration or total current density in semiconductor is contributed by both electron and hole. Okay. So carrier transport phenomenon of only two phenomena occur involved in the carrier transport. There is one is a deep velocity phenomenon, and another was a diffusion phenomenon. Deep velocity phenomenon, suppose this is a semiconductor, or initially this is suppose metal. Without application of external electric field means voltage. Okay, this electron inside the metal, I am talking right now metal, I will go to the semiconductor, they randomly move. Once we apply the electric voltage or electric field, they will align and try to move particular direction. Electron try to move and it will give the current. So in semiconductor, there is a positive hole, negative electron. They are randomly inside the metal without application of external voltage or electric field. Once we apply the voltage or electric field, suppose this is a positive pole, this is a negative pole, then what happens? The electron move toward the positive pole and hole move toward the negative pole. And this, as a result, this will give a current density or current, and which is contributed by both electron and hole. Clear? And another phenomenon is a diffusion phenomenon. What do you mean by diffusion? In order to make you understand, I am drawing a diagram. This is suppose room. This is my room diagram. This is my room. Suppose up to this level you fill up a water. This is my room, and the room is partitioned into two parts. One is this part and another part, and one room is totally filled with the water, and another remaining part of the room, the other part of the room, the beyond partition, is a vacuum. Then what happens after few minutes or few hours? Then water will move from this room to this room. Through what? Through the wall. So gradually it come out and finally come out the water from that room to this room. And this phenomenon is known as a diffusion. And this is occurred. Why? Because of gradient of water. Similarly in semiconductor, now you consider semiconductor. Semiconductor electron, this part, this high concentration of, forget about electron hole. This semiconductor is partitioned into two parts. So one part, suppose concentration of electron is this, and another part concentration of electron or hole is very less. This is semiconductor. The concentration in one side is very high, and concentration in other side, maybe electron, maybe hole, whatever it is, I don't know. So concentration in other side is very less. As a result of this gradient in concentration, the concentration from higher concentration region move toward the lower concentration region to make it balance. This phenomenon is occur in semiconductor, which is known as a diffusion phenomenon in semiconductor. So current is contributed by current density or current in semiconductor is contributed by both diff current and diffusion current. However, the diffusion current contribution is very, very less significant as compared to the diff velocity. Diff current. Okay, so that's why we mostly focus on the diff current, not diffusion. But when we calculate it, we have to encounter all the mechanism. Okay, now I am going to calculate the diff velocity of electron, not diffusion, but if you have to analyze the diffusion current, we later come. Okay, as per the syllabus, I am focusing on the diff current. So diff current, you have already studied NAVD. You have already studied AC current. So this is a current density. Current density is always reactive. Remember, J is always vector. J is equal to I by A. But current, this is a vector quantity. This is scalar quantity. See, although current has magnitude as well as direction. How can you find out the magnitude? If you give a multimeter in a circuit, you can find out the value of current, RMS value of current. This is current value you can get, and direction, in which direction current is moving, we know. But although current has magnitude as well as direction, it is always considered as scalar quantity. Why? Because current, see, a quantity to be a vector, it must have magnitude as well as direction. This is a necessary condition, but not sufficient condition. Sufficient condition is that it must follow the law of parallelogram of vector. Suppose, simple example. Suppose moi chuli dikol rakhise, kanfuli pinise, chuli dikol rakhise, a photo loisu, devili moi swali komni nohoy. In many other conditions I have to satisfy, then I will become a current. Similarly, in order to a quantity to be a vector, it must follow the law of parallelogram vector, although it has magnitude as well as direction. Current does not going to follow the law of parallelogram vector. Why? You see, according to the law of parallelogram vector, suppose this is A, this is right, and this resultant vector are equal to A plus B. See, law of parallelogram vector tells that if two consecutive sides represent two vectors, their resultant vector must be represented by the diagonal element. That means R equal to A plus B. But in case of current, suppose this is it. In case of current, this is I1 current, this is I2 current, this is a resultant. And these all are copper wire. Suppose I am putting here current source. This is a current source. I am putting battery or something like that. I am putting a current source, allow to move current from here to this direction. Okay. And these all are copper wire. This is 5 ampere current. This is also 5 ampere current. And then along this line, according to the law of parallelogram vector, how many current will follow? According to 5 plus 5, 10 ampere current. Okay. But why it will 10 ampere? It will move only 5 ampere current. But according to law of parallelogram vector, 5 plus 5 it will be 10. But because this is a copper wire, this is copper wire, the amount of current will be same. Also may not be same, because if the resistivity of this wire, although they are copper wire, if the resistivity of this wire is greater than this one, then current will be less, 4 point something. That means current is not going to follow the law of parallelogram vector. That's why current is a scalar quantity. But current density J is a vector. This is I scalar, but area is always vector. Remember, area is always vector. Area is given by length and breadth. Area, suppose this is my room. This is x direction. This is y direction. Suppose in order to calculate the area of the ground plane, then what happen? Length into breadth, it will be like this. So area vector will be perpendicular to the length as well as breadth. So area is a vector. So any quantity, scalar quantity divided by vector quantity, or any scalar quantity multiplied by vector quantity, it will be always vector quantity. So current density is vector. Forget about that. So this is equation in semiconductor. This equation you have already studied in ACES. This is for metal. But when you talk about a semiconductor, there will be two carrier. One is an electron, one is a hole. So I can modify this equation like that. I will modify this equation. This equation I am writing in case of semiconductor. J equal to Ne Vd, is it okay? Plus Pe Vp, is it okay? N is the electron concentration. E is the charge of electron. Vd is the deep velocity of N, and V dp. Vdn, this is a suffix, okay? Don't confuse. Vdn, d is suffix deep velocity, N is the deep velocity of electron, D suffix deep velocity, P is for hole. So this is a current in semiconductor. Why E is here? E is the charge of hole. Charge of hole is equal to the charge of electron. That's why I put in common. So I can simply write so E NVD plus P dP. Simply V dN, V dP. Okay. Deep velocity of electron, deep velocity of hole. Now another term you have to study the mobility. Mobility is represented by mu, deep velocity by electric field. But in case of here there is a two such here. There will be two mobility, mu n, V dN divided by E, mu p mobility, V dP by E. Okay. What is the physical meaning of mobility? Mobility measure how well semiconductor transport electron from one point to another point. I will tell you in detail. So mobility defined when we apply semiconductor. Suppose this is a semiconductor, we apply electric field. Electric field, don't confuse, electric field means voltage. When we apply voltage, how fast, how good this semiconductor transport electron from here to this point. Suppose this point is a positive point. So electron will move from here to there, toward positive. So what is the characteristic behavior of semiconductor? The mobility measure how after application of voltage, how well, how good this semiconductor transport electron from here to there. This measured by the mobility. Okay, and how fast, how well this semiconductor transport hole from here to negative pole. This will measure the mobility. So mobility, if I replace the mobility equation, then you can this is E, this is E, this is E is a common, and mu n E plus P mu P E. E is the common. I'm taking in the outside. Is it okay? This is the current density in semiconductor. Clear? So J equal to E n mu n P mu P E. E is the applied electric field or voltage. Now you see current density in semiconductor. E is charge of electron is constant, 1.6 into 10 to the minus 19 coulomb is the constant. N is the number of carrier. Mu n is the mobility of electron. P is the number of hole, and mu P is the mobility of hole. Now what you can understand? So current density in semiconductor is contributed by both electron and hole. Also, this current density is depend on the mobility of the semiconductor. If mobility is high, then semiconductor is good, although it less number of carrier. If mobility is very less, then semiconductor is considered not good. Okay. Why? Suppose I am giving an example, and in between this, suppose you have a two semiconductor. Suppose semiconductor A, semiconductor B. Okay. You have two semiconductor A and semiconductor B. Suppose semiconductor A has a carrier 10 to the power 19 electron carrier. Okay. Semiconductor B has a 10 to the power 13 electron. So you obviously, because high number of electron means high current. Okay. You can say, but this is not exactly true. And this mobility is suppose 100. This semiconductor has mobility 100. This semiconductor is mobility is 50. So mobility measure how well semiconductor transport electron from here to there. So if the semiconductor, although it has a high number of electron, but it cannot transport electron from one point to another, then you will get a less current. So performance of the semiconductor will be less. Another example. So according to this view, this is suppose ulta, I am telling ulta, 50, this is 100. This, although it has less number of electron concentration in semiconductor, but it is high mobility, so this will be better semiconductor. Although it has a high number of electron, but mobility is less, so this semiconductor has lesser performance compared to the B. Another example. We are two friends. Suppose Anil Hazarika and another person. I have 2 lakhs rupees in my account, and this Roman has 5 lakhs rupees in his account. I invest 2 lakhs rupees in the market. He has 5 lakhs rupees in his account, but he has invest only 1 lakh rupees. So finally, if when the business get profit, then I will get more profit, because he has less invest 1 lakh rupees. He has already invest 1 lakh rupees, so he will get less profit. I will get more profit. So although I have only 2 lakhs rupees, but although he has 5 lakhs rupees, but he has invest only 1 lakh rupees, but I have 2 lakhs rupees in my account. I have invest whole 2 lakhs rupees. I will get more profit. Similarly here, this semiconductor although has a less number of carrier, but mobility is high. High means it has high capability of transport electron from one point to another. As a result, I will get a high current. So B is a better performance as compared to the A. Okay. So this is the equation. Again I know J equal to E. I am writing again N mu N plus P mu P. This is the equation in semiconductor. But V equal to Ohm's law, you remember, V equal to IR Ohm's law. Also J equal to sigma E Ohm's law. Both are Ohm's law. Ohm's law. Do not confuse. Why both are called Ohm's law? You can derive this equation from here, from this equation, or this equation you can derive from this equation. That is why both are known as the Ohm's law. If I replace this equation, J equal to sigma E, this is sigma, not 9, okay? Sigma E into N mu N plus P mu P. E cancel. So conductivity E N mu N plus mu P. This is the conductivity in semiconductor. Okay, clear? Now the N is the number of carrier in semiconductor. You have to calculate using density of cell. Similarly, P is the number of hole carrier in semiconductor. You have to calculate using density of state function. That's what I'm deriving the last derivation. Okay, this is the density calculation. And conductivity, this equation, resistivity is opposite to the conductivity. So it will become E N mu N plus P mu P. Okay. So high concentration of electron, high concentration of carrier in semiconductor is a less resistance. If this semiconductor concentration is very high, the resistivity of the semiconductor become less. Okay. Now Hall effect, I will not tell Hall effect in this class, because you already, I will tell you in the next class. Hall effect. So what is the Hall effect? There is an experiment in the BSc level. Okay, Hall effect, you see. Suppose we know this semiconductor, we can calculate the carrier concentration in semiconductor, carrier concentration of hole in semiconductor. We can calculate using density function, and current density we can evaluate using this equation. But before that, suppose if I giving you this is what. Suppose I tell you this is a semiconductor, but I don't know whether it is N-type semiconductor, P-type semiconductor. I have already told you there is a 2 type of semiconductor. So in order to determine this semiconductor whether it is P-type or N-type, I have to experiment Hall effect. Hall effect will determine the type of semiconductor, number 1. Number 2, you can calculate the conductivity of semiconductor, resistivity of semiconductor. You can calculate. This experiment is known as a Hall effect. I will not discuss today. I will give you an overview how Hall effect work and what is the simple mathematics involved with the Hall effect. After that I will directly move to the transistor mechanism. Okay, thank you.